When will the recording be posted? It should be posted by the end of the day. I will say, if because Dr. Kim can sometimes take a little bit. So I post these videos on YouTube just because like it's easier to post there. Um and the YouTube is just through this SDSU email. So if you want to see the video earlier, I'm gonna post it. So maybe just look up like H. Glazebrook on YouTube or something and it might show up. Okay. So we're going to start with chapter 28, fundamentals of circuits. So this chapter is actually going to be pretty quick, but there are a couple things you can get confused on. So I want to iron those out today. So just to start here, just with Ohm's law. So Ohm's law. Oh, sorry, there's a question in the chat. How everyone is studying. I guess anyone else can answer that in the chat, but yeah, I'm gonna keep going. Okay. So basically, Ohm's law says that potential difference is equal to I times R. Potential difference is just the usual potential difference we've been talking about this whole time. I is the current that flows through the circuit. It has units of amps. R is going to be your resistance. And it has units of ohms. Cool. So the first thing I want to teach you is how you want to go about drawing your current and sort of different ways of labeling it. So I have a circuit here. The first thing you want to do, and it's just good practice, is um, you want to draw the current going from the positive to the negative end of the battery. That's just usually how we write it. So I'll start at the positive end, and I'll go all the way around to the negative end. Oh, pretend I go all the way around. But so it's going to be going something like this. And I'll just label that as I. One thing you want to note, if you have a circuit with no junctions like this one here, so it's just one wire, then you're only going to have one current. So you only ever have one current per wire in your circuit. Okay. Now on the circuit on bottom, I'm going to do the same thing, but you'll see what happens if we do have a junction. So I'm going to start at this positive end right here. My current's flowing out. But then when I reach this junction here, what happens is your current splits off. So let's say it splits into current I1 and I2. So here's I1, here's I2. This I2 is going to flow all the way around. And then when I1 and I2 meet back up, they're going to turn back into I. So there's a couple things there. First, the current flowing into and out of that battery has to be the same. So if I labeled this current I as flowing out, I also has to flow back in. So that's the first thing. Current is conserved. The second thing, when this current from the battery split off into I1 and I2, there is something special about that. It's called Kirchhoff's node rule or Kirchhoff's current law, something like that. I'll just put it here. You're going to use this a lot for circuit analysis. So Kirchhoff's current law. And I'll show you how to use it when we do an example in a sec here, because I know a lot of these are hard to see without examples. So Kirchhoff's current law, all it says is that the sum of the currents flowing into a junction, so sum of the currents flowing in equals the sum of the currents flowing out. And just to put a note here, a junction is just anywhere where two or more wires meet. That's all a junction is. So in this case, this is a junction right here. And this is also a junction down here. And just as an example, if I wanted to use Kirchhoff's current law on this top junction, all I would say is all the currents flowing in is just I, and the sum of the currents flowing out is I1 plus I2. And so we're going to use those type of relationships to solve for the current in a circuit. Cool. So that's Ohm's law. That's generally how you want to write your currents, how you want to draw them out. Just know that when you reach a junction, your current splits, and when it splits, the current flowing in has to equal the current flowing out. As long as you keep those things in mind, you'll be all good. One more thing I want to say is there's a couple different ways to write the direction of the current. And when we go on to Kirchhoff's loop rule, I'm going to show you a way that's a little bit easier for me. So in this top circuit up here, let's say for instance, instead of drawing the current as just flowing this way, so instead of drawing it as flowing down, another way of saying that is it's going positive to negative and positive to negative on these resistors. Again, I want to state that I haven't changed the physics of anything. Current flows from positive to negative on the resistor, so this is just a way of noting that my current is flowing downward. And this positive negative notation is going to help later on when you do your loop rules. Cool. Does anyone have questions about that? Because I know that part's a little weird. Okay, this will all make more sense when I do an example, I promise. Okay. Before I go more into Kirchhoff's loop rules and stuff, I will just touch on equivalent resistance. So you'll use equivalent resistance usually in situations where you have a really simple circuit. So if I have a circuit like this, it's just one circuit and there's just two resistors in series here, then it's really easy to turn those into an equivalent resistance. The way you do that is R equivalent just equals R1 plus R2. And that's for resistors in series. You can tell if they're in series if they're along the same wire. So these are along the same wire, so they're in series. One thing I want you to note is resistors in series also share the same current. Cool. So I'll put a note here. Current is constant for resistors in series. Cool. Now down here we have the parallel case. I'll put series up here so that we know. Here's the parallel case. So I have two resistors. They're not on the same wire, and so I know they're in parallel. And so if I want to create an equivalent resistor out of those two, all I have to say is that that equivalent resistance is 1 over R1 plus 1 over R2 to the negative 1. There's different ways of writing that equation. This is the most general way and the way I would use. And then one important thing to note, the potential difference is constant for parallel resistors. So potential is constant across resistors in parallel. So general rule, if you see a resistor that's this simple, or if you see a circuit that's this simple, especially if it only has one battery, your best bet is to use equivalent resistance to just simplify the circuit. Anything more complicated, if you see more than one battery, or if you see like a lot of resistors, usually at that point you want to use Kirchhoff's loop rules. What if they're more in parallel? Oh, that's a really good point, actually. So I just gave you an example with two resistors. Just know if you have more, I'll actually put a note there. That's a great point. If there's more resistors, you just do the same thing. So if we had 5 resistors in parallel, it would be 1 over R1 plus 1 over R2 plus 1 over R3. You get the gist. Same thing for series. You use it for however many you have in series. So good point, Enzo. Thank you. And again, you'll use these for simple circuits. Anything where you have more batteries or really complicated geometries, then you're going to use Kirchhoff's voltage law, which we're going to do an example of right now. Before we do, I'm just going to write down what Kirchhoff's voltage law is. So all it is it says the sum of potential differences across each circuit element in a closed loop equals 0. And I'll put that in writing here. So the sum of potential differences across each circuit element in a closed loop is 0. Cool. And by the way, when I say circuit element, all I mean is a battery is a circuit element, a resistor is a circuit element, resistor, and also a capacitor is a circuit element. So those are just all circuit elements. They're going to have different potential differences across them. And if you sum those up in a closed loop, they always have to equal to 0. The reason for that is just conservation of energy. Cool. So with this particular chapter, it's a lot easier to see how to use these in examples. So I'm just going to go straight and do an example of using Kirchhoff's loop rule. Cool. All right. So I have an example here. It looks like we have a 12-volt battery connected to 2 resistors in parallel. So usually for a problem like this, it's asking us find the current across the 20 ohm resistor. If you're more comfortable with your equivalent resistances, you do see that those are in parallel. You can add them together and solve the circuit that way. I'm going to show you how to solve it the Kirchhoff's law way though, and I'll show you that I think it is a little bit easier. So what you want to do, step number 1, is you always want to choose the direction of your current. So choose direction of your current. So here's kind of the funny thing about it. You can choose any direction you want. What will happen if you choose the wrong direction? If you choose the wrong direction, then you will end up with a negative current. You end up with negative current. If you see that negative current, all it means is you chose the wrong direction and you need to flip it. That's all. So you can choose any direction, it doesn't matter. But if you end up with a negative current at the end, you know you need to just flip the direction you chose. That's all. So I'm going to go about choosing my direction. It is kind of best practice, as I said, start from the positive end of the battery. So I'm going to label this current I. I reach a junction here, and I know if I reach a junction, my current splits. So that's going to split off. That's going to split off into I1. I'll write it down here. I1 and I2, let's say. And then as it comes back, it's going to turn back into I. Okay, so I chose my current directions. Hopefully those are the right directions, but if they're not, all that's going to happen is I'll get a negative. I'll know I chose wrong. All right, step number 2 is choose the direction. So when I say loop, all I mean is you're gonna uh, you're gonna start basically at one point on a closed loop, and then you're just gonna walk either clockwise or counterclockwise. The best part is it actually doesn't matter. You can choose whatever direction you want again. So you can choose any direction you want. Choose any direction, either clockwise or counterclockwise. But there is one important thing I have to say. Whatever direction you choose for one of the loops in the circuit, you have to also do for the second. So you cannot change the directions of your loop. If you choose clockwise, you have to stick with clockwise. If you choose counterclockwise, you have to stick with counterclockwise. And that's really important. So I'll put a note. Need to stick with your choice. With choice. Okay. With that said, doesn't matter what I do. So I'm just going to choose clockwise, let's say. So that just lets me know that I chose clockwise. And now before I go into solving for this, I'm going to show you that notation for noting the direction of the current. So if current is going through this 10 ohm resistor, if it's going down, it's going from positive to negative. And for this 20 ohm resistor, if it's going down, again, it's going from positive to negative. And I'll show you right now why that makes your life a little easier. Cool. So we chose our current direction, we chose our loop direction. Now we just need to apply Kirchhoff's loop rule and we'll be all good. Let me move this down a little bit. Okay. So step number 3 is apply Kirchhoff's loop rule. So I'm going to start with this very leftmost loop. I'm going to pick a point and I'm just going to walk around the circuit clockwise until I get back to that point. So I'm walking around clockwise. I reach this battery. It's taking me from negative to positive. So it's increasing current. So that's going to be a positive 12 volts. Again, I'm going from negative to positive. So it's increasing. That's positive 12. I keep walking around my loop, keep walking around my loop. I reach this 10 ohm resistor. It's taking me from positive to negative, and so it's decreasing. So that is negative. And now here's where we use Ohm's law. Because we're talking about the potential difference across the resistor, technically that'll be negative current flowing through the resistor, which is I1, times the resistance, 10 ohms. And again, that's just because the potential difference across that resistor is just I times R. And we know that the current flowing through it is I1. And technically the resistance is 10 ohms. Cool. And then I go all the way back. I formed my closed loop, so I know all those potential differences have to equal 0. So that's my first Kirchhoff equation. Now I'm going to go to the rightmost loop. I'm just going to pick an arbitrary point and walk counterclockwise around until I get back to my starting point. As I'm walking around, I reach this 10 ohm resistor. It's taking me from negative to positive, and so it's increasing my voltage. So that's going to be positive I1 times 10 ohms. I keep walking around clockwise. I go from positive to negative on this 20 ohm resistor. if it's taking me from high to low, that means it's decreasing my voltage. So that is negative I2 times 20 ohms. And again, make sure you have that I2 in there because that's the current that's flowing through that resistor. I keep walking around, I'm back to my starting point. So I know that all those potential differences have to equal 0. So we're in a closed loop. Cool. So from here, we have all of our equations and we just have to solve. So from here, we're just going to solve. So we're trying to find I2 because that's the current flowing through the 20 ohm resistor. From here, all I'm going to do is add 20 I2 on both sides. So we have I1 or 10 I1 equals 20 I2. And we also know that 10 I1 equals 12 from that top equation, which means that I1 just equals 12 over 10, which is just 1.2 amps. So I'm going to plug that in for I1 on this side. So we get 10 times 1.2 amps divided by 20. And that's going to equal I2. So I2 is just 12 over 20, which is just 0.6 amps. And now when you put that in, you're just like, okay, the current flowing through the 20 ohm resistor is 0.6 amps. Cool. Any questions about that? Walk through that last step. The solving step, or like step number 3 or step solving step. Okay. For the solving, honestly, it's totally there's like a lot of different ways you can solve it. So, um, that was the way that made more sense to me, but there's other ways to do it. So I don't want you to get stuck in thinking that this is like the only way to solve it. Um, the whole point is that you just have two equations here. You're trying to solve for I2. So all I did was I looked at equation 2 here and I said, okay, I'm going to add 20 I2 on both sides. And then that's how I got this equation. And then I took my top equation here and I solved for I1. Then I just substituted I1 back into here and divided by 20 on both sides to get I2. For Taylor, for step number 3, the starting point, don't worry about it. I'm just kind of using that to get you to think about starting at a point and walking around. So you can choose wherever you want to start. I did choose these corners here. So I chose to start here for my first loop and end back here. So that's where I started first. And then I chose to start here for both of those. Cool. If we have time at the end, if we have time at the end, I'll do example 2. Right now I'm going to move on to RC circuits just to make sure we get to everything. Okay, so moving on with chapter 28 stuff, that was all the circuit analysis. Now we're going to go into something called RC circuits. All an RC circuit is a circuit that has a resistor and a capacitor in series. So it's going to look something like this. Here's your capacitor. Here's your resistor. So there's some very special things about about this particular, there we go. So there's some special things about this circuit. So things about basically, um, the whole point is you can charge a capacitor using a battery, and then when you disconnect that battery, it'll discharge, and we can model that discharge and that charging. So if it's charging, which is something it'll state in the problem, by the way, you want to use this equation here that says that the charge as a function of time, where this is the charge on the capacitor, is going to be increasing as the initial charge, 1 minus e to the negative t over tau, where tau is r times c. So R is the resistance in your circuit, C is the capacitance, and then again, this is just the charge as a function of time on your capacitor as it's charging. One thing I want to note, there was a homework problem where you had a lot of capacitors and a lot of resistors. You always want to take it down to C equivalent and R equivalent whenever you're solving for one of these. So you want to take it down to R equivalent and C equivalent for your tau. Cool. So one more thing, you might also want to talk about how the current is changing. For charging, the current is going to be I naught, which is just whatever initial current you have, e to the negative t over tau, where again, tau is just R times C. So for these problems, honestly, just put these equations on your sheet. Definitely note which ones are used for charging and which ones are used for discharging. And then whenever you see that problem on a test, then just go right to these equations and basically just, it's kind of a plug and chug situation. I will go over an example though, just so you know how to use them. Before I do that, I'm just going to write the discharging equations. So we have charge as a function of time for a discharging capacitor is Q naught e to the negative t over tau. And the current is still, it's negative Q naught over RC e to the negative t over tau, or just I naught e to the negative t over tau with a negative sign. You'll notice that the equation for charging and discharging are the same. Honestly, for charging, you're not really going to use this current part. You'll usually just use current for the discharging, just for most problems. But just keep that in mind. Any questions about that? Okay. Oh, the equations are the same. For tau, yeah, sorry. For like tau is always R times C. My bad. But here, let's go into an example. Okay. So this is an example you might see on the test, especially since Dr. Kim likes more of the sort of short answer multiple choice. So this is a good question that he might put in there. So we have a 20 microfarad capacitor and it's discharged through a 60 ohm resistor. It's asking us how long does it take for the discharge current to reach 50% of its initial value. So first things first, it says discharged, so we know we have to use our discharge equation. I'm going to take the negative sign out. That's not important. Sorry, your textbook adds it, but the negative sign doesn't matter. Okay. So we're going to use our discharging equation, which is IT equals I naught e to the negative t over tau. Again, this is your current as a function of time. As a function of time. This is your initial current. Initial current. And then this exponent here, t is just how much time has passed. Tau is just that constant that equals R times C. Yeah, and so that, honestly, I'm tempted to, this equation's in your book, the Q naught over tau stuff. And I think there was one problem that sort of had you find I naught using that. Um, for most purposes, though, you're really only going to use this equation here, but this was just in your textbook, so I wanted to put it in there for completeness, but I also don't want to confuse you guys. So look this up. It's in your textbook, but you'll rarely use it. You're mostly just going to use this guy right here. So I'm sorry if that's confusing, but look it up in your textbook. You're mostly going to use this, but just know that that's there if it ever asks you to find the initial current, which it rarely does. It's usually going to be a problem like this where they say the current has reached 50% of its initial value or 25% of its initial value. It'll usually be a problem like that. Cool. Okay. So first things first, it's asking for the time for the current to reach 50% of its initial value. So what that means is that I at some time t has to equal half of its initial value. So 0.5 times I naught. That's what it means to be half of the initial value. So what I can do is plug this into our equation, and we have 0.5 I naught equals I naught e to the negative t over tau. All right. So the next step here, I see that the I naught on both sides is going to cancel. And so I can take those out. And we have 0.5 equals e to the negative t over tau. Cool. From here, you might remember when you work with exponentials, how to simplify them. If you take the natural log of an exponent to the x, then it just equals x. So what I'm going to do is take the natural log on both sides. So we have natural log 0.5 equals natural log of e to the negative t over tau. This is going to stay ln of 0.5. But like I said on this side, the natural log of this exponent is just going to be whatever's up here. So we have negative t over tau. And again, what we're trying to solve for is the time it takes to discharge to 50% of its initial value. So I want to solve for t here. To do that, I'm going to multiply both sides by tau. So I'm going to get t equals ln 0.5 times tau. And I'll put my negative sign there as well. Cool. Now, before we solve this, we just need to find out what tau is. And we know that tau is R times C. Resistance in this equation is 60 ohms. Capacitance is 20 microfarads. One thing to note here, this is in microfarads, but it always has to be in the base unit. So we're going to have to take that micro out. So we're working with this. Tau is going to be 60 ohms times 20. Micro is 10 to the negative 6. So that's 10 to the negative 6 farads. Which is 0.0012 seconds. So I know it's weird, but tau, or I'm sorry, seconds? Yeah, it is seconds. Tau is in units of seconds. The reason for that is if you have an exponent here, t over tau, whatever's in the top of that exponent, it actually has to be unitless. And so time is in seconds, so tau also has to be in seconds for those units to cancel. That's also why you have to take this to be ohms and farads, because that's the only way it's going to equal seconds. Cool. So T just equals negative ln 0.5 times 0.0012 seconds. And that's just 8.3 times 10 to the negative 4 seconds. Notice that the negative sign is going to cancel because the natural log of anything less than 1 is going to give you a negative number. Any questions about this? Okay. This is a really important problem to understand because I guarantee you there's going to be at least one problem on it because it's really easy to put into a test. As long as you remember discharging and you remember just a little bit how to deal with exponents, then you'll be all good. Cool. So now this is just the last part of chapter 28. And this is power in circuits. It's nothing really new. I'm just going to give you these equations. So all I'm going to say is there's a concept of the power dissipated by a resistor. And that power we note as P subscript R. And that's going to be equal to the current that flows through the resistor times the potential difference across it. Another way of writing it using Ohm's law is it's the current flowing through the resistor squared times the resistance, or even the potential difference across it squared over R. So these are just three different ways of finding the power dissipated by a resistor. When it comes to finding the current and the potential difference, you're going to use Kirchhoff's loop rules to find those. And then once you have those, you just use this equation to find the power. So that's why I'm not going too deep into it. It's just an equation you want to have. And you use all the rules we just learned to find current and potential difference. And then you can just use those to find what the power is. And I'll just put in here, there also is an equation for the power supplied by the battery. And that's usually just noted as P bat equals the current flowing out of the battery times the EMF. I did have a question about the EMF, so I'll just put a little note here. EMF, which we usually note with this epsilon here, all it means is the potential supplied by the battery. So all it is a potential difference. It has units of volts, and it's pretty much just another name for things just to kind of confuse you for some reason. I don't know why we have it, but don't let it confuse you. It just means the potential difference provided by a battery. So when we saw in the previous examples, we saw a battery and it had like 9 volts. That just means the potential difference supplied by the battery is 9 volts, and we call that the EMF. So it's just a name for the potential difference supplied by the battery. Don't let it confuse you. With that said, that's the end of chapter 28, and we'll move on to chapter 29 if no one has any questions. Cool. All right. How do we tell if a problem is using ideal batteries or real ones? I thought battery was watts. You, mm. The potential difference supplied by the battery is volts. The power supplied by the battery is watts because the unit of power is watts. But when it says 9 volts is the EMF, that is not power and that is not watts. How do we tell if a problem is using ideal batteries or real ones? Oh yeah, for internal resistance and stuff. Um, I'll put a little note here, actually. That's a good point. So that's one part I skipped over. Basically, I'll put a note here. You're always going to use ideal batteries unless they tell you otherwise. So always ideal batteries unless told otherwise. And when I say ideal batteries, I just mean have no internal resistance. Um, Nothing changes though when it comes to the oh we isn't that Kirchhoff's rules completely applied to ideal batteries voltage? Yeah, but so the thing with I also see your point, Manishka. Um, the whole point and the reason I didn't kind of go into this is if you have real batteries, all that means is that battery has some internal resistance, and we basically just model that as another resistor in the circuit, and everything else is the same. What I mean by that, usually a real battery is drawn like this, so it's kind of big. It has this battery portion and this little resistor portion. Here's your plus minus. Internal resistance usually has a little R, and then it goes on and it makes whatever circuit you're doing. This is big R. Here's EMF right there. So it'll be pretty easy to tell if it's a real battery problem because you'll literally hear the word internal resistance or it'll say real battery. So it's going to make it extremely obvious if you have to. But I just kind of want to emphasize that nothing in this problem changes. You're going to do your analysis just like before, but now you just act like you have an extra resistor here that has a resistance of little r. But nothing in the physics of the problem changes at all. It's almost like you just add another resistor. That's it. Okay. But yeah, it'll be really easy to tell. And for the most part, you're going to just do ideal batteries. There might be like one problem on internal resistances, and it'll be very obvious when you have to use that. Cool. All right. So that's chapter 28. And oh, Christina asked if there's internal resistance, would any of the equations change? No, the equations wouldn't change per se. You just have to make sure you add that in here. Um, There are some instances where people have this equation for internal resistance, and so they think it's something separate. I'll just show you real quick what I mean. So here's R, here's EMF. So here's a battery. This is the ideal case. This is the real case. It's just a circuit with a battery and a resistor. For the ideal one, if we did Kirchhoff's law, we know there's a current flowing through here, and we just are going to use Ohm's law, and we're going to say the EMF is equal to the current times the resistance. That's all. For the real case, all we have to do is act like this is now a circuit that has two resistors. And if we did our loop rule, here's our current flowing through I. All we have is epsilon, which is the EMF, minus I little r minus I big R equals 0. Again, I used Kirchhoff's voltage law. I summed up all the potential differences, and I just treated that internal resistance as just another resistor in the circuit. So in the ideal case, the current in that circuit just equals EMF over R. For the real case, the current equals EMF over R plus little r. So none of the physics changed. All that happens is now we just have like an extra resistor in the system. That's all. Okay. So that's all chapter 28. It's pretty much all circuits. Now we're completely switching gears to magnetic fields. So magnetic fields are um, they're really similar to electric fields, and a lot of the equations we go through, I'll try and, as I go through it, sort of give you an idea of what the analogous variable is for electric fields. So, without further ado, bring this down. Okay. So the magnetic field we usually note with a B, and it has units of Teslas, which is just this big T. Now there's one equation called the Biot-Savart law. Biot-Savart law. And it basically is going to give us the magnetic field due to moving point source, moving charge. So the whole deal with magnetic fields is you can't have a magnetic field unless you have a charged particle that's moving. So if we do have a moving charged particle and we want to find the magnetic field that it's producing, we can find that as mu naught over 4 pi times Q V cross R hat over R squared. And I'm going to go into this in some more detail. Okay. Again, this is called Biot-Savart law. Just to draw a picture so you can see what I'm talking about. Say we have a charged particle here. It has some charge plus Q, and it's moving with some speed. Let's say that's V. All I'm saying is I can find the magnetic field produced by this moving particle at any point in space. What you do have to do is find out which point in space you want to find the magnetic field. So I can choose any point. I'll choose a point P here. And I want to just kind of describe what these R's and R hats are. So in Biot-Savart law, if I want to find the magnetic field here at point P, that distance r is just the distance from my charge to point P. So that's r. So I'll put a little note. Distance from your moving charge to point of interest, where you're trying to find your magnetic field. I'll also say this mu naught here is just a new constant of free space, similar to epsilon naught for electric fields, and it equals 4 pi times 10 to the negative 7 Tesla meters per amp. Again, Q here is the charge of your particle in units of coulombs. V is the speed it moves with in meters per second. And then I want to talk about what this thing up here is. So this is a cross product, if you remember from 195. And it is kind of special in that it's a cross product with a unit vector. So if we have, just to make it more general, if you have two vectors and you take the cross product, all that means is the magnitude of one times the magnitude of the other, sine of theta. I just completely made up where V is pointing. This is just completely all made up. I just wanted you to see like some sort of diagram. So if you have two vectors, take the cross product. That means it's the magnitude of one times the magnitude of the other, sine of the angle between them. So usually if you want to solve using the Biot-Savart law, you'll do velocity crossed with r hat. R hat is going to be the vector, the unit vector that points from your charge Q to your point P. So it points along your distance r. For pretty much, for most practical purposes, it's going to be 90 degrees. And so what's going to happen is you get magnitude of the speed, magnitude of r hat, and then that sine of theta is going to be sine of 90 degrees, which is just 1. And then last thing, the magnitude of a unit vector is just also 1. So this v cross r hat usually just turns into regular speed. I just wanted to put a note in there. I will say more than likely he won't have you use Biot-Savart law on the test, but just in case you had trouble on the homework, there's that. Cool. Um, from here, before we go into example 6, I'm just going to give you, these are basically just equations for the magnetic field in certain geometries. What is the law that's boxed? Biot-Savart law. So it's this guy right here. This is all Biot-Savart law. It's a way, again, of finding the magnetic field due to a moving charge. Cool. The rest of the equations I'm going to give you is basically just going to be the magnetic field in certain geometries. It's very similar to when we did the electric field of certain geometries, like the electric field from a sphere, the electric field from a wire. It's very similar to that, but now we're going to talk about magnetic fields. And actually, before I do that, sorry, I got to talk about the magnetic force, my bad. So the magnetic force is actually called sometimes the Lorentz force. It's F sub B equals Q V cross B. Again, this is going to be for moving particles. So charged particles. Oop, my bad. This is the charge of your particle. This is your speed. And this is your magnetic field. So what you would do here is if you wanted to find this force, you would just do, this is just going to simplify to QVB. Again, the reason being that sine of 90 degrees is going to be 1, and you know that the force, the velocity, and the magnetic field are all going to be 90 degrees from one another, and you'll just use this to solve. F sub B. I think I should low-key expand on that a little bit more, sorry. I'll pull a little note here, and it is a little bit weird. The force, the speed, and the magnetic field are all 90 degrees from one another, always. So that's why we use the right-hand rule, which again, I'm going to go into in just a little bit. Just know you'll use this equation here, and all the equations we use, you'll use that to find the magnitude of either the force or the magnetic field, and then you'll always use the right-hand rule to find the direction. That's a good point, Mariana. You're pretty much never going to have to, especially on this test, you're not going to ever have to do a cross product. You're always just going to do V cross B equals VB sine theta. And then that sine of theta always goes to 1. And so it's just V times B. So you're pretty much always going to use this equation here. I just kind of want you to see the most general form. Okay, so that's magnetic field of a point charge, magnetic force on a point charge. Now we're going to switch gears into some geometries. I'm going to give you the equations for the two most popular geometries you're going to see. One is just a infinite wire. So we have a wire here. We have a current flowing through it. And again, all current is moving charge. And wherever we have moving charge, we have a magnetic field. So there's current flowing in this wire. Let's call it I. And I want to find what the magnetic field is at point P above it, where the distance between the wire and that point P, let's say, is A. Again, I'm just going to give you this equation. I just need you to kind of know which situation to use it. The magnetic field at that point P is mu naught I over 2 pi A. This is the current flowing through the wire. This is the distance above.
Ceilings, all these systems, they have to be fire retardant proposals, right? There has to be fire retardant on that.
Yeah, not low. For the finite wire, yeah, I can give you that equation as well, because I know that one comes up. So this is for the infinite wire only. So whenever you see the word very long wire, that usually means infinite, and then you can use this equation. So infinitely long wire. And again, you're going to use that to find the magnetic field at that point. If you want to find the direction, you have to use your right-hand rule. And I guess now is as good a time as any to show you how to do it. Pretty hard on Zoom, but I'll do my best. So basically for the right hand rule, you want to put your thumb along the direction of the current. So honestly, we're just going to do a whole thing here. I'll do a whole thing. Yeah, I'll do a whole thing down here about the right hand rule. Because I know it's like it gets confusing. Okay. So the first thing is there's not like 1,000 right hand rules. There should only be two. The first right hand rule you're going to use whenever you see charged particles with some velocity. So charged particle and velocity. The second right hand rule you're going to use whenever you see current. So one of them's for charged particles, one of them's for current. For the one where you have a charged particle with some velocity, I'm gonna, I guess, draw it out a bit. I don't know how to do this. Okay. For the one with velocity, what you want to do is you want to put your thumb along velocity. So your thumb along the velocity. Here, I'm gonna turn my camera on real quick and show you. Mm. So your thumb goes along velocity. So wherever it is, my thumb just goes along it. Then the magnetic field is going to be my index finger. So I'm just going to make a gun, thumb along the velocity. My pointer finger is now pointing in the direction of the magnetic field. So thumb velocity, index finger, or pointer finger, whatever. Pointer finger is the direction of the magnetic field. Now, if you also want the direction of the magnetic force, you're going to have to use your middle finger. So thumb velocity, pointer finger is magnetic field. And now I'm going to stick my, sorry, I don't mean to like, that's so funny. Then you stick your middle finger out, and that's going to be in the direction of the force. And you're going to make sure that your thumb, pointer finger, and middle finger are all orthogonal to each other. They're all 90 degrees. So I'll put a thing here. Middle finger is the direction of the force. So again, with all these problems, you're going to use the equations to find the magnitude of anything you're trying to find. The direction's always going to be given to you with your right hand rule. If you're doing charged particles with velocity, thumb goes along the velocity, pointer finger goes in the direction of the magnetic field, middle finger goes in the direction of the force. Cool. The second situation you might see is, let's say, a wire with some current flowing through it. If you see that, it's actually a little bit easier. So all you want to do is put your thumb in the direction of the current. Thumb in direction of current. And then once your thumb is in the direction of current, you actually just want to wrap your fingers around your thumb like this, and that'll tell you that the magnetic field is spiraling along your current just like this. Cool. So wrap all your fingers in direction of magnetic field. Cool. So those are the two right-hand rules. You'll use one for charged particles, one for current. And I'll go back up here to our example to show you what I mean. So let's say you were actually given this problem. It's an infinitely long wire. That's your point P. You used this equation here to find the magnitude of the magnetic field. That's a good point. I'll get to that, Adam. Thank you for mentioning that. I did forget. I'll put a note, Adam made a good point. Everything we described is for positive charges. It'll be opposite for negative charges. Opposite. When I say opposite, by the way, I should explain that. You're still going to put your thumb along the velocity, but it's just the direction of the force is going to be flipped. So I should actually explain that better. So this is all for positive charges. For negative charges, direction of force flips. Now, for current, we're always going to assume that the current is positive charges flowing, and so you don't worry about anything to do with negative, positive charges or anything. So for right hand rule number 2, don't even worry about it. For right hand rule number 1, look, is it a positive or negative charge? And that'll basically tell you which way the force is pointing. Cool. It's pointing like that if it's a positive charge, and if it's a negative charge, you just do this, but then the force is pointing the opposite way. That's all. These are the only 2 rules you have to worry about, I'm going to say with confidence. Are we allowed to put these on our cheat sheets? I don't know. Dr. Kim seems like uh really specific about his cheat sheets, so I feel like I can't answer that because I don't really know. No? Okay. Yeah, I don't know. He's I don't know. He's really weird about his cheat sheets. Cool. But yeah, it shouldn't be too hard to memorize, especially after you do some practice. Okay. So again, this is for an infinitely long wire. That's a good way of finding the magnitude of the magnetic field. Just to finish out, if I wanted to find the direction, all I would do is put my thumb along the direction of the current and then wrap my fingers around. So if I were to do that, it looks like the magnetic field is going in a circle around this wire, and it's going this way. So what that means is it looks like it's coming out of the page at my point P. So if you like did this, it's coming out of the page at point P. Notice if my point P was on this side, then the magnetic field direction would actually be into the page. So where you put your point of interest actually does matter. Cool. So that is for an infinitely long wire. I will put a little note here. If you have a finite wire, it changes a little bit. For a finite wire, it's B equals mu naught I, sorry, mu naught I over 4 pi A. Everything's still the same there. A is your distance above the wire. But now you have sine theta 1 minus sine theta 2, where those are the angles from 1 and 2 tips of the wire to your point P. So I can draw that out just a tiny bit. So like if this is your wire, this is point P. This is theta 1, and this is theta 2. I doubt you'll have to use a finite wire equation on the test, but I just put that in there since I forgot who asked, but since someone asked about it. Cool. So next there's the curved wire. This is just the last more popular one. Oh, for finite wire, it's just the direction of the magnetic field is exactly the same because current just flows this way. And so if I did my right hand rule, let's say magnetic field will be out of the page here into the page here. So if your point's up there, it's into the page. If my point's down here, yeah. So it's the exact same thing for infinite. Doesn't change. Okay, the next most popular geometry you are gonna see is the curved wire. So we have a curved section of wire. And again, I'm giving you guys the like two most popular ones you're gonna see, and I think those are the ones that are most likely to be on the test. But there are other geometries, so just take note of that. So we have a curved section of wire. It has some current going through it. We want to find what the magnetic field is at point P here. This guy is going to be theta. A is going to be basically the radius of this section of wire. So the magnetic field at this point, B, just equals mu naught I, where I is the current flowing through the wire, divided by 4 pi A, where A is just going to be the radius of that curvature, times theta, where theta is just the angle that arc curves with. Cool. Again, put this on your sheet. Just make a note of it so that if you see that geometry, you could be like, okay, I know what to do there. Um, and if I wanted to find the direction here, again, I would just take my thumb, put it along the direction of the current. And what I see is it's going to be coming out of the page on this side, and it's going to be going into the page on this side because it's going in a circle around it, just like this, using my right hand rule. So that means if I wanted to find the direction at P, it would be into the page. Cool. Mhm. Okay. Um, yeah, I know that part's a little weird. So for the right-hand rule of a current, you put your thumb along the current and then the magnetic field is wrapping around it. And so whenever you have a wire, here's the current. I'll try and draw this really nice. So the magnetic field is going in a circle around the wire. And if I put my thumb along the current, it looks like that magnetic field is going clockwise. And so I'm going to draw my arrows noting that it's going in a circle this way. And so if my point P is like, if it's up here, the magnetic field at that point is coming at me. And so that's how I know it is coming out of the page. Down here, it's going away from me. So that's how I know it's going into the page. So this is a way of kind of writing that loop without writing the loop. That makes sense. I know it's kind of weird to wrap your head around, but awesome. So I do have an example here. I don't know if it's worth doing. Do you guys think this is worth doing, or should we just keep it on? I know this was like, I think it's a homework problem. Okay, if no one particularly wants to see it, I'll just move on so we get some more stuff. All right. So I am gonna write, there's something called Ampere's law. It's basically analogous to Gauss's law, but for magnetic fields. It's a way that you can find the magnetic field from a geometry. So notice how in the geometry, like the infinitely long wire, the curved wire, stuff like that, I just gave you what the equation is. And for the most part, just having that equation is fine. But Ampere's law is a way, Ampere's law is a way of finding what those are. B dot ds equals mu naught I enclosed. So as you can see, it looks very similar to Gauss law. And again, this is just a way of finding the magnetic field from a certain geometry. So I'm going to use that to find the magnetic field through a wire just so you can see where it comes from. Okay, let me just erase this. Sorry. Okay. So let's just say we have a wire here and it has some current flowing through it, which we're going to call I. Again, this is not something you're going to have to do on the test. I just want to show you where this comes from using Ampere's law. So you have an infinitely long wire, has a current flowing through it I. What I'm going to do is I'm going to draw a cylinder around it, similar to how we did for Gauss' law. That cylinder is going to have a radius of A because that's at my point P. And then I'm just going to write my Ampere's law equation. So first things first, you're never going to use this integral because the magnetic field is always constant. So we take it out. That's just going to be the magnetic field. Here's mu naught. The charge enclosed is just I. And then all this ds is it's just going to be the circumference if you were to walk in a line around your object. So I have a cylinder here. If I were to walk all the way around, it would just be the circumference of a circle, which is just 2 pi a. Mu naught I enclosed, which is I. If I divide both sides by 2 pi a, I get b equals mu naught I over 2 pi a. So that's how you use Ampere's law. Again, I'm not too sure how much you guys have gone into it, so I just wanted to show you that little example and just notice that that's how I found the magnetic field for an infinite wire, and that matches what we have up here. Let's see, so that's that. I'm gonna post this so you guys can see it anyway, but I do have like some suggested problems that are in the textbook for chapters 28 and 29. So take a look at those. Obviously, do your own studying, but I just thought those problems were particularly good. But that's the end of chapter 29. So we will go into chapter 30. Does anyone have any last minute questions before we do? If the examples are not done, if you don't try it, could we still have the solution and work for practice? Yeah, I think I have the solution somewhere. Yeah, I'll just post them with the notes. Yeah. Yeah, this is basically just think of this as just the proof, but honestly, just write down this equation on your sheet. And whenever you see the wire, just use that. Cool. Is there anything else I want to talk about? Actually, okay, I will put a little note. Sorry, there's one more thing I just want to give you for chapter 29, and that's that Lorentz force that was Q V cross B. We use that for charged particles. But if you have wires, we're also going to have a Lorentz force, and that's going to be equal to the current times the length of the wire crossed with the magnetic field. You're going to use this for current carrying wires. Yeah, I know this, it's a lot of stuff. Um, those are the first two chapters. My advice would be um to basically read through the textbook, take notes on the chapters so like you don't miss anything, you have all the notes. Make a formula sheet with those notes, and then use that formula sheet and nothing else when you do the homework. And when you do the homework, try not to just do every single problem because you'll burn out quick and a lot of it's just going to be fluff. So maybe just choose like 5 problems from each homework that you thought were the hardest or maybe that are going to be the most applicable on the test. Do those. And then once you're done with all that, then I would suggest looking at textbook problems. And again, I thought these textbook problems were a good place to start. So maybe look at those. Yeah, I think there is going to be induction on test. That's chapter 30, which we're about to go into. All right. So yeah, that's my advice, but you'll be all good. And this is just the last little bit of stuff for induction. And it's honestly, it's not going to be too much. This part's pretty quick. So this is chapter 30. We're going to talk about Faraday's law and induction. Okay. So just diving right into it. Faraday's law is pretty much um, it's a phenomenon where if you have a changing magnetic field, it's basically going to induce another magnetic field that opposes that change. And that's going to cause some things that are pretty interesting. So Faraday's law just states that we have an induced EMF. And all I mean by that is an induced potential difference. And that's going to be equal to N times d phi sub b dt. And I'll explain each of these terms. First of all, N here, that's the number of turns you have in your coil, because we're going to be working with coils. For the most part, if you don't see anything about the number of turns, it just means that you only have one loop and N equals 1. But just know this is the most general formula if you have multiple turns. So N's the number of turns. This guy up here is called the magnetic flux. Magnetic flux. And it's very similar to electric flux. It just equals the integral of the magnetic field through some area. And for the most part, you're not going to use this integral. You're just going to use B dot A, where B is the magnetic field magnetic field in Teslas, and A is the area. And then this here, this derivative with respect to time, it just means if your magnetic flux is changing with respect to time, then that means you're going to have an induced EMF. So this is just a derivative with respect to time. Cool. So just to draw you an example. So let's say we have a loop here. This loop has some area, let's call it A. And we know that area is just going to be pi r squared. Let's say there's a magnetic field going up through it. So if this is just the case, then there's going to be no induced EMF. The reason being, the magnetic field and the area are constant with respect to time. So if we took a derivative with respect to time, it would be zero. There's no induced EMF. But now if the magnetic field or the area is changing with respect to time, then you're going to get the EMF. So either the problem is going to say area is changing with time, or it's going to say magnetic field is changing with respect to time. And when it says changing, it's going to specify whether the magnetic field is decreasing or increasing. Any questions so far? Because I know this is a lot. Okay. All I've said so far is if you have a changing magnetic flux through a loop, then that's going to cause an induced EMF. But now I kind of want to talk about how that induced EMF is going to work. So, as in what direction is the induced magnetic flux going to point? So, this is the law of induction, or you might have heard it as Lenz's law. And it's the direction of the induced current. And when I say induced current, I mean we're inducing an EMF, and that EMF is in turn going to induce current to flow. That induced current is going to act such that the direction of the induced current acts to oppose change in the magnetic field. So a lot of students get confused on this part. And what they do is if they see a problem like this and they see, oh, my magnetic field is pointing up. If it's changing, that means I have to have my induced magnetic field be induced point downward, which is not exactly the case. And I'll explain sort of why. So I'm going to give you guys kind of general rule here. So we have our loop. We have our external magnetic field pointing up like this. Now, let's say the problem says B, or this magnetic field, is now increasing. So it's getting higher and higher and higher. So our induced magnetic field, which comes from our induced current, is going to oppose that change. So if this external magnetic field is increasing, we want to basically take magnetic field away. So in this case, I do want my magnetic field to point downward, my induced magnetic field, which I'll call B induced. Once you have the direction of your induced magnetic field, then you can find the direction of your current. So in this case, if I put my thumb along the loop, if I were to go, let's say, in a counterclockwise direction, and I wrapped around, then you'll see that in the center of that loop, the magnetic field will be pointing up. If I was to go in a clockwise direction, the magnetic field would be wrapping down. Since I want the magnetic field to wrap down, that tells me my induced current has to be going clockwise. So this is the direction of I induced. Cool. All right. We have another loop. Same direction for our external magnetic field. But now I say that that external magnetic field is decreasing. So it's getting lower and lower and lower. And since Lenz's law says our induced magnetic field needs to oppose that change, we want to increase it. In order to increase this external magnetic field, we need to place our induced magnetic field in the same direction. So this is B induced. So you see how that part can get confusing? If our external magnetic field is decreasing, we want to add to it, so our induced magnetic field actually points in the same direction. So that's a part that some students can get confused on. And then if induced magnetic field is pointing up, that means our current is pointing counterclockwise. Our induced current is counterclockwise. So that's the way you can find the direction of your induced current in a loop. Any questions on that? Yeah. Yeah, so the direction of what I do and what I think is easiest in this problem is you find the direction of the induced magnetic field, and then you use that and your right-hand rule to find the direction of the current. The reason being, it's easier for me to see if the external magnetic field is increasing and I want to add magnetic field or subtract magnetic field. It makes sense to do the direction of that magnetic field first and then use your right-hand rule. And how I want to do it is, if you could see my camera, if I'm going in a loop, like the loop is this plane, I put my thumb along the direction of the current and I wrap around. If I'm wrapping around my loop here, if I'm going counterclockwise, it looks like my magnetic field is going to wrap and point up through the loop. So that's going to be for the second example here. That's why I did that. For the first example, where I want my magnetic field to point down through the loop, if I'm going, if I'm going clockwise, it's pointing, oh, sorry. If I'm going clockwise, it's pointing down through the loop. I don't know if this is the best way of saying it. Basically look at your right hand rule, thumb goes in the direction of the current, and you have to figure it out from there, but I know it's not the best. Does that help at all? Okay. So I swear almost done. Um, way almost done. So there's just one more thing with induction, and then we'll move to inductors super briefly, and then we'll be all done. So There is something called motional EMF. Basically, all that is motional EMF. It's just an example of induction where you have a conductor moving through an external magnetic field. Again, this is just a special example of induction. You'll know it's motional EMF if you see a conductor and it's moving with some speed through a magnetic field. So let's say this is our conductor here. It's moving with some speed v. And then it's moving in an external magnetic field that's pointing into the page. And let's say the length of our conductor here is L. So as this conductor moves through the magnetic field, it's going to have an induced EMF across it, which means it's almost going to become like a little battery here. That induced EMF is going to be equal to the speed it moves with times its length times the magnetic field. So again, this is a very special case of induction. If you ever see a conductor moving in a magnetic field, you know, okay, it has an induced EMF now, and it's equal to the speed it moves with multiplied by the length of the conductor multiplied by the magnetic field. Cool. The last little bits of this chapter are just small things. Mm, mm, uh, I do have a question for you guys. Because I don't know how much you went into inductors. Did you guys have RL or RC or I'm sorry, RL or CL circuits on your homework or in class at all? Does that ring a bell for anyone? Like inductor resistor circuits, transformers, I'll definitely go over transformers. But you think so? Okay. RL sounds familiar. Okay. So it's like you're kind of learning it like last minute, like today, kind of. Okay. I'll put it in here so you have it since it's on the test. But yeah, definitely look in the textbook notes. It's not anything too complicated, but yeah. Okay. So I'll do a little spiel on what an inductor is. Inductor. Okay. So an inductor is just a new circuit element that we're introducing. So when I say circuit element, again, I mean the circuit elements you've seen up to now are batteries, capacitors, and resistors. Now we're adding something called an inductor. The way it's written in a circuit is as a loop like this. And it's going to have, just like those other circuit elements, its own unit. It's called inductance. We note it with an L here, inductance. And it has units of henries, which we just denote with an H. So inductors, you'll learn more about it in class, but just know that they work through induction and they basically can store energy in your circuit. Um, and they can also provide resistance at the same time. Through induction, you'll learn it in class. I'm just going to give you sort of the equations you need to use. So the most popular thing you'll see is an LR circuit. By LR, what I mean is inductor resistor. So you'll have a resistor here and an inductor. Yeah, there's R, there's L. And it's actually going to be very, very similar to um, to your capacitor resistor circuits in that the current that's being held by the inductor is going to change as a function of time, and it'll discharge in the exact same way. You'll have some initial current, and then it'll discharge as e to the negative t over tau L, where this tau L is L over R. So as you can see, very similar to an RC circuit, but now we have inductors here instead of capacitors. Um, that's pretty much it. When you go into class in the textbook, you'll learn a bit more about inductors. I think there's only one more thing I want to say with inductors. And I did mention that they can store energy. And so similar to capacitors, you can find the energy stored in an inductor as UL equals 1/2 Li squared, where L is in the inductance in units of henries and I is the current flowing through it in units of amps. And if you want to find the energy density or the energy stored in the magnetic field, that's across the inductor, because again, inductors work through magnetic fields and through induction. That's just 1 over 2 mu naught times magnetic field squared. So energy stored in B field. Okay. All right. So that's pretty much all I have. We went through chapters 28 through 30. Again, I do have some suggested studying on 28 and 29. And yeah. And Manishka, I think for the homework, if I understand correctly, Dr. Kim accidentally added a question from chapter 31 on there, and I think he took it off. I'm pretty sure. But does anyone have any questions about the test or concepts, anything? Damn, he put 2 questions on there. You hate to see it. Mm. UL sorry, is the energy stored in the inductor, and it has units of joules. UB is energy stored in the magnetic field of the inductor. And it actually has units of joules per meter to the third. It's an energy density. Energy density. Oh, rip. I did not put transformers. Let me put a little note about transformers. Thank you for reminding me. Yeah, transformers may show up, but they're not too hard. Transformers will basically be V2 over V1 over 2 over N1. So basically you'll have 2 inductors or transformers, and one of them is going to be operating at potential 2, the other is at potential 1. And the ratio of V2 over V1 equals the ratio of N2 over N1, where N2 is the secondary number of coils, N1 is the primary number of coils. V2 is secondary potential difference. Primary potential difference. This is pretty much the only equation you need for transformers. That's why I didn't go on a whole spiel about it, because pretty much just use that. For RL, why is LT not negative for discharge, like the RC discharge? Oh, I mentioned, I'm sorry, I totally kind of sped past that. Um, there shouldn't be a negative sign for the RC discharge.
Good
I took
morning.
that away. That was my mistake. So they should both be positive. Am I doing the final exam review too? Uh, maybe. Because these review sessions are just like um something I do separately for the class. So I think I probably will, but I just have to make it. Any other questions? Okay. Okay. Well, um, all right. Well, I'll stop sharing. Yeah. So